Hello, good evening. Welcome to Unacademy. This is VV Live, right? So, if you are not yet subscribed for Plus, Unacademy Plus, I recommend you and I suggest you can use for this VV Live code for get good concession, and you are going to get advantages of all these given here, like a premium content at affordable price, structured live classes plus dedicated live doubt clearing sessions, and also quizzes will be conducted at regular intervals for self analysis. Students, and you can get complete preparation, and number of batches are provided from this Academy Plus, and also test series and DPPs will be given daily practice papers. Full length marks will be conducted, and can get complete analysis. These all facilities or advantages, whatever you may think, you're going to get under single subscription. So for that, use this code. And also, students, you see here in this Unacademy Plus, you're going to give a better and good education with 20 plus top educators, right? 10 plus batches you are given, 250 plus courses, and apart from that 2000 plus lessons and many more every day are going to add, right? Hope you are understood for this. Okay, if you are aspirant of EAMCET, JEE mains or advanced, whatever it may be, even medical stream, so you can use the best use of this one, Unacademy Plus, and for that VV Live is the code. Hope you understood. And now today's our session is Nuclei Part 2. Students, today's our session is Nuclei Part 2. Nuclei Part 2. We are already discussed Part 1. In that, what we are discussed about properties of the nucleus. Students, what we are discussed properties of the nucleus. So mainly in that we are discussed for radius of the nucleus, density of the nucleus, and the constituents of the nucleus. Okay, all about this we are discussed, and of course we are ended with one concept called a mass defect, and now today we are going to take up that again. Okay, from that we have to continue actually binding energy concept we have to discuss. For that I am just recalling for this mass defect using this mathematical equation. Delta M is nothing but mass defect. Mass defect is nothing but, it is nothing but, mass defect is nothing but difference of, difference means minus sign, difference of mass of all the nucleons inside the nucleus. Say this is the nucleus. Inside the nucleus what are present, students? Protons and neutrons are present, as we know. These as nucleons. So mass of all these. So mass of all these nothing but number of protons into mass of each proton, isn't it? Plus number of neutrons. Number of neutrons means what? So it's A minus Z, isn't it? A minus Z gives the number of neutrons. Next, minus, number of neutrons and mass of neutron minus actual mass of the nucleus. This is the mass defect, and already we have discussed, right? This is usually in kgs. Mass is expressed in kgs, right? Kgs like this if I write. But concentrate this unit kg. Okay, just focus on this. Usually masses of subatomic particles, subatomic particles won't be in kgs. This won't be in kgs usually, very less na. So these are in atomic mass units. These are expressed in atomic mass units. And also we can write 1 AMU is equals to 1 U. 1 AMU is equals to 1 U. We can write like this. Students, you have to understand this, right? You have to concentrate here. 1 AMU. Sir, what is 1 AMU? 1 AMU is nothing but a very small amount of mass, students. 1 AMU is nothing but 1/12 of small mass, like that I told. How much small? It is nothing but 1/12 of mass of carbon C612 atom, stable carbon, this one. As you know, carbon has isotopes like C612, C613, C614. For carbon dating, C614 we are using, already we are discussed in previous class. Fine. Now we are going to calculate for 1 AMU. So 1/12 of mass of C612 means, students, 12 by Avogadro number, mass number by Avogadro number. So now for that, if you are calculating, 12 gets cancelled, 1 by n, Avogadro number means right, okay, 1.603 into 10 power 23. This is the number, friends, right? So now for this, if we are writing 1 by 1.603 to 10 power 23 can be written as right, 1.6766, like that it comes 67 into 10 power minus 27 kgs, friends. So 1 AMU is equals to this many kgs. 1 AMU is nothing but these many kgs, right? Now, as we know the famous relation given by Einstein, okay, here masses are there in that relation. Einstein's mass energy equivalent relation, if I write, you will understand very clearly how we are going to use these units, right? So E is equals to delta mc square. This is the famous relation given by Einstein, which means both mass and energy are interconvertible. These two are interconvertible, right? Interconvertible means mass can be appear as energy, and also even energy can also appear as mass. That is the mass energy equivalence relation. This is said to be mass energy equivalence relation, right? Now in this equation, here you can see this delta m. Suppose if this delta m is given in AMUs, usually in case of modern physics, in case of subatomic particles, what happens, this mass will be given in AMUs generally. So if this mass is given in AMUs, right, 1 AMU I am taking into c square. C means 3 into 10 power 8 meters per second, it is to be squared, 1 AMU. So like this will be in joules. And now here I am writing the relation between electron volt and joule. 1 electron volt is equals to 1.6 into 10 power minus 19 joules. Students, this is the relation between electron volt and joule. So from this you can write 1 joule is equals to 1 by 1.6 into 10 power minus 19 electron volts. Suppose if I write here capital M means mega, means million. So here I should divide with the 10 power 6 usual, definitely. So for that, if I write, this goes into mega electron volts. So for that I am writing here. So 9 into 10 power, this 3 square 9, 10 power 16, right? 1 AMU, for 1 AMU I am writing, divides by, right? In AMU if I want to express, what I have to do? Students, in AMU if I want to express like this, simply the electron volts. In electron volts if I want to express, divides by 1.6 into 10 power minus 19. Suppose if I multiply here with 10 power 6, the denominator, here I can write mega. So altogether E, if you are calculating, right? If you are calculating for this E, it comes, energy comes like a 931.5 mega electron volts, students. So 1 AMU, see here, 1 AMU is equals to 931.5 mega electron volts. Students, here what you have to understand is, whenever 1 AMU mass is going to convert into energy, that equivalent energy is nothing but 931.5 mega electron volts. From this I am clearing again, both mass and energy are interconvertible. It means 1 AMU is equals to 931.5, means this is the relation what we have between those two, like this, right? Now actually in yesterday's class we discussed for mass defect, delta M is equals to, right? Just now also we are saying in the first one itself, right? This equation you see here, if it is given, masses are given in AMUs, this mass of proton, mass of neutron and mass of the nucleus. Here delta M mass can be written, right, like this, into 931.5 mega electron volts. Means this one energy, this energy can be written like this. One second, this energy can be written like this. E is equals to, now what I can write is, this E is equals to delta M into C square, right? So if this delta M is in AMUs, right, this energy can be written in mega electron volts. If we are multiplying with 931.5 mega electron volts for delta M. So delta M into 931.5 is the energy. Okay. So this energy actually we have to call it as a binding energy. So already we are saying for mass defect it's nothing but okay difference of masses of all the nucleons to the actual mass of the nucleus, like that we have discussed. So that difference where it is going, this difference where it is going, right, where it is going, this mass is only appearing as energy. That energy is said to be binding energy. That mass is said to be binding energy, right? So likewise we have students. So while calculating for binding energy, you have to keep these points in mind. Binding energy is delta M into C square. If this delta M is given in kg, energy will be in joules. If this delta M is given in kg, this energy will be in joules. If this delta M is given in AMUs, atomic mass units, what you have to do? Into 931.5 you are taking, it goes into mega electron volts. These 2 points you have to keep it in mind, friends. Likewise, because whenever one AMU is converting into energy, that is equal to this 931.5 mega electron volts. That is the reason why we can say like that. So next, binding energy per nucleon concept I am taking. Binding energy we are saying binding energy per nucleon. Students, as we know, one chemical element representation XZA. In this Z is nothing but protons number, A is nothing but mass number, right? And A minus Z is equals to neutrons number. This is the neutrons number. Binding energy per nucleon decides the stability of an atom. This decides the stability of an atom. What we can say is like this: stability, more stable or less stable, like that we can. You see here, for example, one element I am considering, that is helium. So in this helium, how many protons are there? 2 protons are there. How many neutrons are there? 2 neutrons are there, right? And suppose if the binding energy, for example, not exact values, for example, binding energy of this nucleus, right? Binding energy of the nucleus is, right, 7 mega electron volts for entire nucleus. This is the 7 mega electron volts. Whereas suppose for another one like lithium 37, for this binding energy per nucleon, what we are writing? Binding energy is this, the binding energy, total binding energy. So binding energy is 7 are there na. So it's nothing but 1 second, students. This are 28 actually. It's of 28 mega electron volts as a whole. And now for lithium 37, if it is of for example I am saying it's of 35 mega electron volts, not exact value this one, rough value I am giving. Suppose if it's of 35 mega electron volts, if it is asked which one is more stable, first one is helium, second one is lithium. By seeing this binding energies here, 28 mega electron volts, here it's of 35 mega electron volts. Generally, if you say more binding energy is there for this helium, that's why it is more stable. 1 second. More binding energy is there for this lithium, that's why it is more stable, like that we can say. But actually stability, binding energy won't decide. What is going to decide? Binding energy per nucleon. Means in order to remove one nucleon from nucleus to the outside, how much energy we have to spend is nothing but binding energy per nucleon. Each and every nucleon, if you want to remove, for each nucleon how much energy is required, that only decides the stability now. Just think of it once. So that is called binding energy per nucleon. So now if you see for these values, binding energy per nucleon for this case of helium and lithium, you see we will write here. Okay, binding energy per in case of helium, what I can say is, it is having 28 mega electron volts total, but it should be shared from this 4 nucleons na. So 2 protons and 2 neutrons are there na. So here 2 protons and 2 neutrons, here 3 protons and 4 neutrons are there. Okay, let it be. Now here 28 by 4, which means 7 mega electron volts, means from each nucleon it requires 7 mega electron volts in case of helium. But coming to this, students, you see, okay, coming to this lithium 37, in this case, what I told, 35 mega electron volts divides by how many? 7. 7 nucleons has to share. So it's of 5 mega electron volts. So per nucleon, per each nucleon, okay, this requires less as compared to this. So that is the reason why what we can say is this one is this helium is more stable than this lithium. Students, this is a very good example, right? Very good example. You have to concentrate on this. Binding energy per nucleon only decides the stability of atom. Okay. Sorry. Now, students, here you can see after this, okay, binding energy concept. I'm going to introduce decay, alpha, beta, gamma particles decay. I'm going to discuss. See here, one radioactive substance is there. One radioactive substance is there. Here is the radioactive substance. What is radioactive substance? Radioactive substance means substance which can emit alpha, beta particles, okay, followed by gamma radiations. Okay, these are the particles. These are the particles followed by gamma radiations. Okay, spontaneously from this it has to emit. So in this direction alpha particles, suppose in this direction beta particles, alpha, beta, suppose gamma particles are gamma radiations are moving like this. So that kind of substance is said to be, okay, radioactive substance. Radioactive material or substance means radioactivity it has to exhibit, right? Radioactivity it has to exhibit. So radioactivity is nothing but the spontaneous emission of alpha, beta particles followed by gamma radiations. Here in this diagram, students, you can see very clearly. Here I am showing for alpha particle in this direction, beta particle in this direction, whereas gamma particle is not deviating in a way. In a straight way it is moving without any deflection. Here actually alpha particle, if it wants to move in this direction, it should be attracted by negative plate because alpha particle is having a positive charge. Alpha particle is nothing but nucleus of helium, right? Whereas beta particle is nothing but it's generally beta negative electron. So it should be attracted by positive plate. This point you should observe very clearly. Whereas gamma radiations are nothing but electromagnetic radiations or waves, I can say electromagnetic wave. So electromagnetic wave cannot deflect to either electric field or magnetic field. Here electric field is established from positive plate to negative place towards left in this given diagram here. So whenever one alpha particle and a beta particle is going to release from the radioactive substance, what are the changes we are observing in the parent nucleus? What I am calling as parent nucleus. Parent nucleus and daughter nucleus. These two names, okay, we can use. Parent nucleus and daughter nucleus. Daughter nucleus. Parent nucleus means what? Students say this is the XZA. This is parent nucleus. From this, one alpha particle is released. Alpha particle means what? Helium-24. Be remember. Alpha particle means helium-24, right? So therefore, here whenever from this X, now this is said to be parent nucleus. Okay, now daughter nucleus is to be formed here. So this is alpha particle. This is alpha particle, right? Remember. So whenever it is releasing like this, we have to check for two things. One is right, conservation of okay, atomic number Z. Okay, this is the first one. The second one is conservation of A, mass number. So for Z means protons number, if I check the conservation before releasing the alpha particle, whatever the number of protons it has in this parent nucleus, the same number of protons it should have after releasing this this alpha particle. So combiningly. So therefore here Z is there. So finally after releasing this alpha particle, what we can write for this case of Y? the protons number. If I write for Z minus 2, if I write for Z minus 2, if I add both of these two like Z plus 2, here see here conservation of Z. Initially Z is there, so this Z I am writing. After that what is happening? Z minus 2, this Z minus 2 plus this plus, and here it is 2. So therefore students, here 2 gets cancelled. It means minus 2 and plus 2 gets cancelled. Z is equals to Z. So therefore I can say it is conserved. Z is conserved. Prandtl number is conserved. Likewise for A. For A we have to write. Here initially what we have? Students, here you see A we have. Initially A we have. Before releasing the alpha particle in the parent nucleus. Now this is the daughter nucleus. This is daughter nucleus. Okay. Now in order to see this as A in this side, so if I write for A minus 4, you see here A minus 4, this 4 is to be added. So therefore A minus 4 plus 4. Now, okay, minus 4 plus 4 gets cancelled. A is equals to A. So conservation of A also obeyed. So therefore what we can say, these two conservative laws, okay, conservation of protons number means conservation of Z and conservation of mass number are obeyed. So therefore this reaction is possible. So in this main observation from this is, whenever alpha particle is releasing from the parent nucleus, in the daughter nucleus, if you observe, its atomic number decreases by 2 and mass number decreases by 4, means 2 units, 4 units, like that we can say. So whenever atomic number decreases by 2 units, its place in the periodic table shifts towards the left by 2 units. As you know that okay, all the chemical elements in the periodic table are arranged in the increasing order of Z. In this direction Z is increasing. Suppose here is our X element initially. Whenever this Y daughter, this is parent nucleus. Now coming to the daughter nucleus, 2 Z minus 2 means towards this left 2 units it should take place. So this is the daughter nucleus. So what we can say, in the periodic table, this is nothing but okay, periodic table. In the periodic table, its place shifts towards left by 2 units. So that is the observation whenever alpha particle is releasing from the parent nucleus. And students, okay, you can ask about a beta particle. Alpha particle is over. Next, what about beta particle? Beta particle is of two kinds, friends. One is, okay, beta minus. The second is, right, beta plus, right, which means this is nothing but electron. Okay, this is nothing but 1 second. Okay, this is nothing but okay, sorry, minus 1 should be drawn now in the denominator. Minus 1 0, this is 1, this is a positron, this is electron, and this is a positron. Now you see, this is electron, this is the positron. As you know, these two are particle and antiparticles, right? Particle and antiparticles, right? This, if it is a particle, this becomes antiparticle, right? Now see here, electron and positron. Usually beta particle, like that, if it is said, you remember that as electron only, until and unless they are mentioning it as a positron. Now let us come to the observation whenever electron is released from the parent nucleus. This is the parent nucleus, and here is the, right, beta minus, or we can say, we can write it as E minus 1 0. So that one I am taking, and it is convenient here. So therefore E minus 1 0 I am writing. So now in this daughter nucleus, here daughter nucleus say Y, like previous, in previous reaction we took it as Y, in the same way. Now it should be the same before and after releasing of this beta particle from this parent nucleus. What has to happen is this conservation of Z should be obeyed. So for that Z plus 1 we should write. So that time Z is equals to this, Z is equals to Z plus 1 minus 1, this plus 1 minus 1 gets cancelled, Z is equals to Z. So therefore conservation of Z is okay, it is followed. Now here if I write A, then no problem, because initially it is A, and after release of this beta particle A plus 0, again you can see this as A only. So conservation of mass number also verified, and in this observation is whenever electron or beta particle is released, there is no change in the mass number. And also here in case of Z, what is happening in the periodic table? What about the position? Initially Z is here. Now finally what happens? Z plus 1. So one place shifts towards right. So in the periodic table, daughter nucleus, this is the daughter nucleus, this is the parent nucleus. So from parent nucleus to daughter nucleus, if you see the position, its place shifts towards right by 1 unit when parent nucleus releases an electron or beta particle. Suppose if it releases beta positive, means positron. So here it is the parent nucleus XZA. Now it is releasing for positron E plus 1 0. Now see students, here you see what happens in this parent nucleus, daughter nucleus. So okay, Z, what should we write? Z minus 1 we should write in order to keep it as Z, and here it is A only. So here observation is, what is our observation? Its phase shifts towards the left by 1 unit. Here is the parent nucleus. Now the daughter nucleus place will be here. So 1 unit, okay, its value is changing towards left, right? So likewise, okay, whenever positron is released, beta plus, okay, beta plus, we can write like this. Particle is released from the parent nucleus, okay, like radioactive substances. Its place shifts towards left by 1 unit. Whenever electron is released, its place shifts right towards right by 1 unit. Whenever alpha particle is released, its place shifts towards okay, Z minus 2. No? This one, 1 second. Z minus 2, right? 1 second. Okay, here is the Z and here is the Y. So therefore, its place shifts towards left by 2 units. Okay, so like this it is observed. And now suppose, for example, we will see one example in this case, right? Suppose uranium 92, okay, 236 is there. From this one alpha particle is released, for example, right? One alpha particle means what? Helium-24. We remember, alpha particle means helium-24, means nucleus of this one. So therefore here what happens in the parent nucleus, you see, so 2 units it should be decreased, so it should be 90. So thorium, it is okay, basically thorium, so 232, like that. One daughter nucleus we can see, right? So any relation you see, like this 2 units it should be decreased here, 4 units it should be decreased. So likewise, okay, and suppose from here, for example, any this thing you can take, parent nucleus you take, like lithium 37 only you take, and it is going to release for 1 electron. What happens, you see, 1 electron if it releases, minus 1 means here what should we write? 4 we should write. Okay, beryllium, right? 4 minus 1, it means 3 only, na? Beryllium, this should be 7. So whenever lithium is releasing for 1 electron, it should release, it should produce for a beryllium, So likewise, alpha, beta, gamma particles. Suppose gamma radiation is coming out, so nothing will change, whether A or Z. Be remember for that. Okay, whether it releases for gamma radiation, like suppose 37 lithium is going to release for gamma radiation, so it should be lithium 37 only. Of course it will be in excited state, right? So likewise, this one we have alpha, beta, gamma alpha, beta decay, and a gamma particle, gamma radiations decay we have. Okay, students, hope you are all understood for this, right? Very simple. Today's our discussion is, okay, it is towards mass defect, binding energy, and alpha beta particles decay. And I recommend you all, you have to use the advantage of this Unacademy Plus classes. And if you are subscribing for this, you are going to get all these benefits, students. Nowadays it is not possible to see all these kind of things in one single package. As per my experience, what I'm saying is, I'm suggesting you please go through it. You please go through it means you have to go for this without any second thought. You please go for this plus subscription, and for that I suggest you and I request you please use this VV Live code to get a 10% discount. Right? Hope you are understood for this. Okay. Okay. Thank you for attending this session.